Hello teachers, welcome to section 13-4, surface areas. When we finish this section, you should be able to understand and explain surface areas of right prisms, right circular cylinders, right regular pyramids, right circular cones, and spheres. So when we talk about surface area, what we're talking about is the outside or the inside of a figure, but it's the surface. So we're not at volume yet. That's the next section, 13-5. So we're focusing on the surface of a figure, okay? So first of all, we want to talk about the difference between lateral area and surface area. Okay, so lateral area is the sum of all the areas of the lateral faces. Okay, so we'll explain that when we look at particular figures, whereas surface area is the sum of all the lateral surfaces and the bases. Okay, and again, I'll make this distinction each time we go through a problem. Now, one thing I really want to point out is when you're talking in this section and talking about surface area, keep in mind you're still measuring area. So area uses units squared. So often we're talking about inches squared, centimeters squared, meters squared. Even though you're talking about three-dimensional figures, and again, we will talk about calculating volume in the next section, but right now we're still talking about area and just area of the surface. So let's start off with the most basic surface we could probably come up with, and that's a cube. So as you can imagine, look at the faces of a cube. How many faces of the cube do we have here? Well, so there's a face there. Now how would we calculate that area? Well, that would be, it's a square, right? So E times E, because this measurement is E and this measurement is E. So E times E would give us E squared. All right. How would we calculate, say, this surface right here? Okay. Again, this is E times E, or E squared. Let's just use all my colors, right? How would we calculate this surface right here? Oh, okay. So E times E would be E squared. Now, how many surfaces do we have here? Or how many faces do we have? It's one surface. You could look at it that way. But how many faces are on a cube? And you would say 6 of them, right? So actually, to calculate this particular surface area would be 6e to the second power. In other words, 6 times the side squared. That would be the surface area. Now, I told you I would talk about the distinction between lateral faces and the entire surface area. In this case, the lateral faces would be this one, 2, and then that side one and that back one over there. Those would be the 4 lateral faces, where the top and the bottom, which are no different in this particular case, would be the bases. Okay, so for a cube, you know, if you only wanted to know the sides, it would be 4 times 6e squared, which would be the lateral surface area. But we have 6 sides, so 6 times e squared. I hope that makes sense. Maybe I'm talking too much. All right, so there's your formula that we just discussed. And notice the net. Now, this isn't the only net. You're going to see this in possibly your first homework problem, that there are different ways to draw the net. But I do like this one. It's the easiest to see that if you folded this up, 4 sides would go up, and then connected to this side right here would be the top as well. So this is a net for a cube. There's more than one. You could find many other possibilities for nets to build a cube. Now let's move on to a right pentagonal prism. So goodness, what is this saying? Remember, we defined prism in a previous section. So a prism has the same base. So here's our base going on here. I'm trying to color it. There we go. There's a base. And then down here at the bottom, there's a base as well. I know we often think about bases being on the bottom, but really it's the top and the bottom of the figure. Notice they match. Now, if we say it's a right pentagonal prism, you know what that means, and there's your little There's your little right triangle designation at the bottom showing you that these sides are completely vertical or they are perpendicular to the bases. So that's what they mean by right, perpendicular to the bases. What about pentagonal? Well, that means there's a pentagon as your base for the bottom and the top of your figure. So how could we break this down? What would the net for this thing look like? Well, if we were trying to write a formula for this, and then I'll show you the net, but if we were trying to write the formula for this, we would have the area of the two bases, right? And then we would add the lateral area. Remember, we talked about what that means or meant just a minute ago. So the lateral area would be this side over here. How many sides do we have, y'all? 5, right? And then the back side, let's just make it about as messy as I can, and then the back side over there. So we have 5 sides going on. Now, what do these sides look like? And let me erase so you can look at this a lot better. So what does a side look like, and do they all look the same? So we can clearly see there's a side right here. I'm highlighting that in my lovely favorite highlighter green shade. There it is. So what shape is that? Looks like a rectangle to me. Will they all be rectangles? And you're thinking, no, that looks like a parallelogram, but it's not, right? This is the two-dimensional drawing of a three-dimensional figure. They are all these rectangles. And notice what's really important here is they give you the base of the rectangle, that's S1, times the height of the rectangle. Now, again, let me take that back. Our pentagon might not be a regular pentagon. So all of the rectangles might not be the same. So when we do the area of the two bases, the bases are supposed to match each other. So we would just do 2 times whatever area that base is. But now the lateral area, if this is not a regular pentagon, then we would have to calculate those separately. We'd have to know more information, but let's think about it. So we would have S1 times H plus S2 times H plus S3 times H plus S4 times H plus S5 times H. That would be the lateral area, all 5 sides added together. And then again, to get these total surface area, we would also have to add the area of the two bases. Now, what does this net look like? And let me get you a real looking formula here. So if I unfolded this, picture this as just a net, a folded up piece of cardstock that was bent and cut out in the appropriate ways. Here you go. Notice there's 1, 2, 3, 4, 5 rectangles. That was the S1 times H. And then you have the top and then the bottom, and what those are the bases of our pentagonal prism. Now the surface area, they said P times H, what in the world is that? Now P is the perimeter, okay? So P is the perimeter, which would be S1 plus S2 plus S3 plus S4 plus S5. If we added all of those together, that would equal the perimeter. So they're saying the perimeter times H, would that work? Absolutely. Look at the formula I wrote over here. That's no different than factoring out an H. Uh-oh. My bad, y'all. Hold on. Let me get my pen working. That's no different than factoring out an H. Okay, and then that would be S1 plus S2 plus S3 plus S4 plus the S5 that ended up underneath, and that is your P. Okay, so perimeter times H, and then plus the two bases, like we said before. Okay, so where P is the perimeter of the base, H is the height of the prism, and B is the area of the base. Now, often these are regular shapes, right? In other words, a regular polygon is what I'm after. So, you know, this is a pentagram, and it is depicted that it's regular, which means all the sides are the same, but that is not always the case, and that could potentially change the way you calculate it. You might have to calculate these lateral sides individually. All right, so let's do a problem. Find the surface area of this prism. Now, again, you can use formulas. You can be glued to the formulas, or you can just calculate each surface and add them together. It really is that simple. So I want you to understand it more than I want you to just know these formulas. So let's calculate the surface area. What am I going to do here? Well, I have for the bases, I have two triangles, right? I have a triangle down here that we need to calculate the area for, and a triangle up here. So it's 2 times the area of the triangles, okay? Plus our sides, right? Now, all of our sides are different. So we have 3 times 10, right, to get that rectangle. And then on the right over here, we have 4 times 10 to get that rectangle, and we have 5 times 10 to get that rectangle. But it does say we can just multiply the perimeter times the height. Will that work? Sure it will, right? Because we have to multiply the height times each one of those separately. We can do that just fine. All right, now, how am I going to find the area of a triangle? You remember, so it's 2 of these. The area of a triangle is 1/2 the base times the height, okay? Now, what's the base? Well, the base is what your height is calculated down to. So our base here, let's call that 4. And the height of the triangle now, okay, not the height of your prism, is 3. So 1/2, the base is 4, the height is 3. And if you need a recap on the formula there, again, this is 2 times 1/2 the base times the height. Just the area of a triangle. Okay, plus, remember this is the perimeter, so 3 plus 5 plus 4, I'm going to write that down to be extreme and show you everything, times the height, which is your 10 centimeters. Now, let's run those numbers. So, 1/2 of 4 is 2 times 3 is 6, so I have 2 times 6, so the area of each triangle is 6, and there's 2 of them, plus the perimeter, 3 plus 5 is 8 plus 4 is 12, times the height is 10. So I have 12 plus 120, which is 132. 132 what? Well, this was all centimeters, and we multiplied centimeter times centimeter right here, if I'm getting detailed about units. And over here, each of those was centimeters, and when you add them together, you just get 12 centimeters times 10 centimeters. So all this is centimeters squared. Now, I warned you about that at the beginning, right? This is area, so it's all units squared. Now, of course, let's look at the textbook version of this, and notice they got the same answer we did in pretty much the same way we did, but they didn't write all over the page like I like to do. But we still got the same thing, and now we've learned to check our work with them, but even more, check their work with ours. And so sometimes we make mistakes and sometimes they make mistakes, but our goal as teachers and instructors is to find those mistakes, understand those mistakes, and help our students out. All right. What does this mean to you when you look at this? Okay, so write regular prisms. These are all regular prisms. Just like we talked about, we just calculated the surface area of a triangular prism. Here we have a rectangular prism. Okay. Here, let's see how many sides. 1, 2, 3, 4, 5, 6, 7, 8. So that's an octagonal prism. I'm not going to count these, but it's more than 8. Okay. Now, what it's trying to show you is that if you increase the number of sides of the bases of a rectangular prism, you're going to approach the idea of a right circular cylinder. Just like when we found, do you remember the area of a circle? Again, let's get your pen working. Okay, so remember when you found the area of a circle? And I talked to you a minute about originally this was approximated with a polygon, and we just increased the number of sides of the polygon until it approached just an infinite number of sides. The same thing with the right circular cylinder. Now, we're not going to have to think about it that way, because what we're going to do is deconstruct that right circular cylinder. What would this look like if I tore it apart? Okay, so let's take a can of soup, right, and tear it apart. So the first thing we're going to do is we're going to take our can opener, and we're going to take off the top. Okay, so when we get our can opener, we take off the top, then we're going to have this piece. And let's take off the bottom too, and we're going to have this piece. So now we have like a tube. You agree? Okay, like a pipe. All right, well, how about we cut right here along that pipe where that dashed line is and open it up? What's it going to look like? Yeah, it's going to look like a big rectangle. right? It's going to try to curl back up on you because it's made out of metal. But let's just pretend like it just bends and lays flat, just like a piece of aluminum foil. Okay, so we have two circles, a top and a bottom, and then we have a side. Is it going to be hard to calculate this area? No, absolutely not, especially if you label everything. Remember the height? Where do I put the height over here? Well, that's the height. Now, how long is this thing? That's the question. We unrolled it. It was the shape of a circle, right, before we unrolled it. Okay, well, what's the distance around a circle? We call that the circumference. Remember, the circumference is 2 times pi times r, or pi d. I like the r. Okay, so this is 2 pi r. The length of our rectangle when we unfold our cylinder is 2 pi r. Well, how about the area of a circle? Remember, that's an r right there, although I didn't do a good job of drawing r. Remember, r goes from the center out. And so the area is pi r squared, and we're going to have 2 of those. Okay, so let's say 2 times pi r squared plus the area of our rectangle over here, which is going to be 2 pi r times the height, which is h. So this is your formula for the area of a right circular cylinder. Now, like always, I like to give you the nice, neat version of this. So here is our decomposed can of soup, right? And surface area is right there. So 2 pi r squared, they wrote it backwards. That is our rectangle. Okay, just to remind you. No, I'm sorry. That is our, just like we wrote it. This is just like we wrote it. This is the area of our lids, or the base. Okay, lid and the base. And 2 pi RH is your rectangle. Now, if you forget, you could totally figure that out without having a formula in front of you. I know you can. Okay, now let's move on to another figure. What about a pyramid? Okay, so again, what I want you to envision every time you see these is you're just trying to calculate the surface area. So again, let's see, I want to know what is the area of this triangle. Let's change colors. And then I want to know what's the area of this triangle. How many triangles do we have? Well, 4 in this picture, right? Because the base of our triangle appears to be a square. Okay, so we have 4 triangles. And we don't have 2 bases this time, we just have 1 base, plus the base. Because the definition of a pyramid is these guys meet at 1 point. Now, picture deconstructing this. Okay, in the picture I'm about to show you, here's what happened. It's like somebody was holding these corners at A, and they blew on it, and they all go flat. Pew, there they went, flat. Right there for you. So this is your surface area. So calculating the area of the base in this particular situation wouldn't be a problem at all. It appears to be a square. But then you've got these 4 rectangles you need to add together. The L value is the slope right here. And a much more appropriate word for that is the slant height. It has a slope. Okay, that's the slant height. So that is not the altitude, which would come straight from A down perpendicular in the middle of your pyramid in this case. So it is the slant height, L, because that's going to tell you how tall that triangle is. Okay, let's keep going with this. So the surface area is going to be N times 1/2 BL. What in the world is that? Okay, so remember 1/2 BL is 1/2 the base times the height of the rectangle. So y'all, this is nothing but the area of your triangle, not rectangle. This is the area of your triangle. What's the N? That's the number of triangles that you have, or the number of sides of your base. Either way you want to look at it, that will tell you how many triangles you had. Plus, remember, there's just a single base we're going to add to that. Okay, so where N is the number of faces, also the number of sides of your base. L is the slant height, okay, and B is the area of the base. The formula for the surface area of a right regular pyramid can be simplified because NB is the perimeter, right? And here is our formula. Let's make sure we understand all this. So the surface area is 1/2 P. Again, that's the perimeter of all of your base sides plus the area of the base. So when you see that capital B, it's talking about the area of the base. One more thing. Remember we talked about the lateral area? So the lateral area would be all 4 of these triangles added together without the base. So just pay close attention when you're doing these problems. Do they just want lateral area or do they want the entire surface area? All right, let's do a problem. It says find the surface area of the pyramid. Okay, so do you remember the formula? So remember it was SA is equal to 1/2 PL plus B. All right, we can do this, right? So surface area is equal to 1/2. P, remember, was the perimeter. So the perimeter is if we run all the way around this thing. So we're going to run 4 centimeters this way, 4 centimeters this way, 4 centimeters that way, and 4 centimeters that way. In other words, 4 times 4 is 16 centimeters. So I'm going to put 16. I'm going to put the units in there just so we can talk about this. The L value, remember the L is the slant height. Do we have that? We're not always given the slant height, by the way. Okay? If you are given the slant height, feel blessed. Sometimes you have to calculate it using right triangles. So here we go. We are literally given the slant height. That's that 5 centimeters. So I'm going to multiply that times 5 centimeters plus the base. Now, when you see B, that is the area of the base. What's our base? Well, it's a rectangle, right? It even says it, right square pyramid. You got to be very clear on what your base is. You don't want to assume anything. And the area of a square is just side times side. So this is going to be plus 4 squared. And remember, it's 4 centimeters squared because I'm trying to use units to really show you that we're dealing with area. Okay, so 1/2 times 16 is 8, times 5 is 40. And remember, centimeters times centimeters is centimeters squared. Plus 4 centimeters squared is 16 centimeters squared. And if these are both centimeters squared, that means I'm allowed to add this 40 and this 16 together to get 56 centimeters squared. And that is the surface area of our pyramid. Now, let's look at the typed up version. I do believe I have that. Yes, there it is, exactly the way we set it up. Whew, this is a problem. Here we go. The Great Pyramid of Cheops, hey, we've talked about this before, is a right square pyramid with a height of 148 meters and a square base with perimeter 940 meters. The altitude of each triangular face is 189 meters. The basic shape of the Transamerica building, so we're going somewhere else with this. So the basic shape of the Transamerica building in San Francisco is a right square pyramid also that has a height of 260 meters and a square base with a perimeter of 140 meters. The altitude of each triangle face is 261 meters. How do the lateral surface areas of the 2 structures compare? This is a lot of information. So what I want to do, I don't even have enough room to work here. So I'm going to do another slide where I shrink all this up. We can find the important parts and see if we can knock this problem out. There it is, all shrunk up. Notice I reminded you of the surface area of a pyramid. Remember, it's 1/2 the perimeter times the slant height plus the base. So let's highlight our important information. So Cheops, I'm going to make pink, is a right square pyramid with a height of 148 meters and a square base with perimeter 940 meters. It goes on to say the altitude of each triangular face is 189 meters. Okay. Then on the other hand, Transamerica. So the shape of Transamerica building is a right square pyramid, again, that has a height of 260 meters and a square base with a perimeter of 140 meters, and the altitude of each triangular face is 261 meters. How do the lateral surface areas of the two structures compare? How about you pause it? This is a really good time for you to work on these two separate problems and make sure you understand using this formula and what you're looking for. All right, did you pause it and try it, or are you just waiting on me? Oh, please don't wait on me. Next time you need to pause it and try it. Or go ahead and pause it. Go ahead and pause it. But we're back anyway. So one thing I want to point out, and probably should have pointed out very clearly before we paused it, notice what we're looking for. And I warned you about this. And this is one of those situations. It says, how do the lateral surface areas of the two structures compare? I'm only interested in the lateral surface area. So we're not interested in the base. You know, like the pyramid at Cheops, the base is just the ground. At the Transamerica building in San Francisco, the base, again, is just the ground. So often the base is not part of your story anyway. It only wants lateral surface. So if I use my formula, remember, that's total surface area. What part of this is the lateral surface? It's that part right there. Again, it's without the base. So first let's do pink Cheops. Okay, so it says the perimeter is 940 meters. That's in our formula. So again, lateral, I'm just going to put S for surface, is 1/2, and the perimeter is 940. If you wanted to look at each of the four triangles separately, you certainly could. You'd have to take 940 and divide it by 4, but I don't see any need for that. Times L. Now again, feel blessed when you have this L value, because often you'll have to calculate that given more information about your base and the height. Okay, so we didn't have to calculate it. We know that this is 189 meters, and that was 940 meters. When I multiply that together, I get 1/2 times 940 times 189, and you probably already have this, 88,830. That's meters squared, right? Because I multiplied meters times meters. All right, now let's talk about Transamerica. So again, we have the lateral surface area. So that's going to be 1/2. Now the perimeter of Transamerica is 140 meters, much smaller, times the height, though, is much bigger. You've seen that picture of Transamerica, or you've seen it in person. It's a huge pyramid, but it's skinny, okay? You got 1/2 times 140 meters times 261 meters. So it's 0.5 times 140 times 261. And I get 18,270 meters squared. Remember, meters times meters, again, gives us meters squared. So how do these compare? Okay, now you set up a ratio. How do the lateral surface areas of the two structures compare? We don't know which one to put on the other. Let's put the bigger one on top, okay? The bigger one is Cheops, right? So if I take my 88,830 meters squared and divide that by Transamerica, which is 18,270 meters squared, that's going to give me a result. You go ahead and do it while I'm messing with buttons. So here we go, 88,830 divided by 18,270 gives me 4.86. Let's just stop it there, okay? The decimal continues. So we could say that Cheops, that's the bigger one, is 4.86 times Transamerica. Okay, and we're talking about lateral surface area. So really, if I wanted to make a good sentence, I would say the pyramid at Cheops is 4.86 times the surface area of Transamerica, or the lateral surface area. Still didn't use all the correct words. Now, would you like to look at their depiction of this solution? Let's check it out. All right, so look, Great Pyramid at Cheops, they took the perimeter and divided it by 4 so you could look at each side separately, but notice they got the same thing. It's the same calculation. When you do 4 times 235, you get 940 back. So that is okay that they looked at it at one triangle at a time. What's up with this 4? There's 4 triangles. Okay, keep going. We take a look at Transamerica. They did the same thing. They decomposed the perimeter by looking at each side. Is that okay? Perfectly. And then they multiplied by 4, which gets us the perimeter back. So 18,270, and I do believe that matches what we have. Okay, and then they decided to do the ratio like we did. We could have done it the other way and say that Transamerica is 1 whatever fraction that may be when you flip it upside down. But I liked this way, the bigger one on top. So the Great Pyramid is 4.9 times, I think we said 4.86. So they didn't tell us where to round, so we just took it out 2 decimal places instead of the 1 decimal place. All right, pretty clear on this, but be careful about when they say lateral surface area versus other things. Okay, now I've reached my 30-minute mark, but of course I have not reached the end of the lesson. We don't have a lot to go, but I do want to talk about cones and spheres, calculating the surface area of those, and do a couple of homework problems for you. So come on back as soon as you can and sit in for section 13-4, part 2, and we'll wrap it up, I promise, with part 2. Hope you have a great day.